Hi everyone, my name is Yasufumi Ogawa from NTT. Today I'd like to share about the experience and effort for implementing DPDK's multiple application on container environment. So agenda. So first of all, I'd like to talk about our background. Why using DPDK, or why using Kubernetes, or why using next one, requirements of our environment. And then I'd like to talk about the container CNIs for DPDK. Then how we using Operator SDK for our purpose. And finally, I'd like to talk about our implementation and demonstration. So background. So NTT is one of the largest operator company in Japan. And we have provided several kinds of services by using several kinds of network components such as load balancer, firewall, switch, so. Now our services are running on the dedicated physical hardware for keeping the service quality and reliability and high availability. But now, now in the cloud era, and we need to shift our service infrastructure to the virtualization environment. But shifting to virtualization environment is one of the biggest challenges for us because it is very difficult to keep the service quality or availability also because virtualization environment is not so stable in the mean. And so for our services, there are several requirements. For example, flexibility for the change of our service network configuration or maintainability. It is very important for operators because we need to provide service by user speedy to meet their requirements. And high performance is also important for us because we're keeping the service quality. And integration with cloud management system such as OpenStack or Kubernetes is also a very important challenge for us. So for the purpose, I have developed SPP. SPP is one of the DPDK consuming application and hosted as one of the hosted project in DPDK. And the key point of SPP is simple and lightweight. So for the purpose, we can use, for example, OVS or SRV, but so such kind of technologies cannot meet our requirements fully because for OVS, performance is not so high actually, and for SRV, maintainability is not so fully meet for operators' requirements because so by using SRV, performance is good, but if we need to upgrade the system or version up, so it is very difficult to upgrade while running the services if we use the SRV. But if we shifted to the virtualization technology, such kind of upgrade is more easy because service system is fully virtualized and easy to configure. And so The SPP is to meet these kind of requirements by implementing with DPDK and as DPDK multiple application. So here is an overview of our SPP architecture. So SPP is implemented as a DPDK multiple application. Its mean consists of primary process and several worker secondary processes. Primary is resource manager, and secondary is worker process. So we have several types of worker process in SPP. One is for simply packet forwarding, or another one is classification, or another is mirroring packet also. So SPP also has a controller for managing the DPDK processes, and it should be kept the booting order. The controller is first, then primary and secondary, and client's application also. So for integration, so we have several choices for integration. For example, for OpenStack, we can implement the network application by using Neutron's ML2 plugins. Or for Kubernetes, we can use Kubernetes CNI or Multus plugin CNI. And we have already released our network SPP by using ML2 plugin technology, and it's called networking SPP. It is enabled to control SPP from Neutron's interfaces, and it's enabled to provide flat or VLAN type network. So in this diagram, it is described the controller node and compute node, and so in controller node, Neutron server is running, and we have implemented extension in the Neutron server as with ML2 plugin, and it's called SPP mechanism driver, and it manages the SPP agent on each of compute node, and by this mechanism, we can easily manage the SPP from Neutron interfaces. And for Kubernetes, we can implement the network application by using Multus plugin and several CNI such as SRV or Batch.io. So left-hand side is the architecture of Kubernetes CNI using Multus. So Multus is for using several types of interfaces from a pod. So without Multus, we cannot use several kind of network interfaces, but Multus enabled to use the several pods. And by using this technology, we can add the DPDK interface to Kubernetes pod. And right-hand side is the example reference architecture of using Multus CNI. In this diagram, there are three types of network interfaces attached to a pod. One is typical bridge interface, and another one is VF by using SRV CNI, and last one is Batch.io interface. So, however, we cannot still implement DPDK's multiple application like as SPP because Kubernetes CNI supports several kinds of network interfaces, but other type of network interfaces cannot be supported yet. For example, ring interfaces or so, and so it is also difficult to manage the multiple application because in DPDK multiple application, booting order is keeping booting order is very important. But this Kubernetes CNI and Multus technology cannot support these features. So we need to implement. We cannot implement if DPDK if using DPDK multiple application. So SPP uses ring interfaces for getting high performance, and Kubernetes CNI does not support the interface yet. But we need to use this ring interface to get high performance for our NFV infrastructure. And here is a result of our simple testing of ring interface performance. So by using a ring interface with container, so we can get easily about 10 gig throughput for 64-byte short packet. So in this test case, we have tested the performance by connecting the container in serial from 2 containers to 10 containers. And even if using 10 containers, there are almost no performance degradation. And this is because we strongly want to use the ring interface as container interface. So, but again, so current Kubernetes CNI cannot support the DPDK multiple application and ring interface we strongly required. And here is a requirement for our system. And first one is define resources such as core or memory assignment because so in Kubernetes it cannot define the DPDK's resources such as assignment of core, assignment of memories or so, and we need to additional mechanism for defining such kind of resources. Next one is define network configurations. So not typical network appliance such as OBS. SPP has original or specific network configuration, but it cannot be supported by using default Kubernetes CNS, and we need to add the additional mechanism for defining our network configuration. And third one is keep the order of booting processes of multiple application. And next one supports several types of network interfaces. Some of them are already supported by Kubernetes, but we need to define additional network interfaces by ourselves. And next one is high availability. And final one is manage versions and phases. It means we need to implement the rolling up or rollback mechanism properly. Kubernetes already supports these kind of features, but not for DPDK multiple applications. And this is a typical use case of requirements. So for higher availability, we need to several nodes and configure the clustering for higher availability. And it's also doing a rolling update or rollback. And keeping boot order is also important. So as I explained, so SPP is consist of primary process and worker secondary processes, and it should be booted in order. And so we need to additional mechanism for keeping the order. And another one is manage several types of VNF in separate pods. So in this case, there are 4 pods. Some one include several containers, and some one include just one pod. But it is different for each of use cases. So for some use case, we can. It is okay to use one pod, including several containers. But in some use case, we possibly need to separate each of container in each of pods. It's very depends on use case, but such kind of granularity is very important for meeting the various use cases. So to define the very customized mechanism on Kubernetes environment, we have used Operator SDK. So Operator SDK is a framework to enable developers to build operator. And operator is application-specific controller that extends Kubernetes to create, configure, and manage instances of complex applications such as SPP. And it makes it easy to manage complex stateful applications on top of Kubernetes. And it is very customizable. And so operator is a combination of CRD and controller. So CRD stands for custom resource definition. So it is a mechanism for extend the YAML definition of Kubernetes. And it means that you can define any of the resources in YAML file and give it to the Kubernetes for managing customized application. And so Operator SDK itself is a tool for scaffolding and code generation to quickly bootstrap a new project. So how Operator works, and operators process connecting to master API and watching for events typically on a limited number of resource types. It means the operator is a component for intermediating Kubernetes and customized application and communicate each other to manage your application from Kubernetes properly. And it's implemented as collections controllers. And running application is terminated suddenly, or for example, performance is suddenly high. So I mean, when the assigning of resources should be changed in such a situation. So it's reconfigure the resources. For example, one of the container is suddenly terminated. Kubernetes and operator try to reboot the process to keep the service. And controllers also checks the current status automatically to find some changes of situation of application to keep the services. Sorry. So then I would like to explain how to develop the customized operator with SDK simply. So there are 5 steps for developing the customized operator with Operator SDK. First one is create a new operator project using SDK command line interface. So Operator SDK provides a CLI for developers to implement your customized operator easily. And next one is define new resource APIs by adding custom resource definitions. And third one is specify resources to watch using the SDK API. And the next one is define the operator reconciling logic in designated handler and use the SDK API to interact with resources. And the final one is use the SDK CLI to build and generate the operator deployment manifest. There are just 5 steps for developing the operator. So here is an example of first step, creating a new project with Operator SDK. So by running Operator SDK new command, it is starting to generate several files as scaffolding. It means by this command, templates are generated automatically. And here is a snapshot of generated files. There is several sources of Go and YAML files. So although there are many files generated, you don't need to care about all of files. So here is a detailed description of generated files. But mainly, you need to care about the controllers and APIs. So API is a file for define the custom resources as you need it. And the controller is operator's logic itself. So if you define the logic in controller, so Kubernetes properly call the functions you defined like as a hook function. It means if some events occurred in Kubernetes, so operators call the appropriate function defined in the controller appropriately. And then after scaffolding, you need to add custom resource definition by by generating API. So if you run operator add API command, so operator SDK generate the template of custom resources. And after generating the template, you just need to the definition of resources, which is defined in YAML file for Kubernetes. And here is an example. So in SPP use case, we need to add additional definitions for defining the DPDK resources, such as core assignment or memory assignment and network configuration. So in SPP case, we need to just add the source port and the destination port simply. And by using this technology, we can define such kind of resources easily. Then we need to add a controller. So SDK also provide the command for generating controller-related source code. And it is also similar to the command for API. And after generating a template for controller, so you can add any of function called from operator over Kubernetes. This is an example in our case. So function for create service or find port, or change the network configuration defined additionally in the left-hand side. And after the defining APIs and controllers, we can define any of resources such as requires or socket name, as you may know, in DPDK's application, can be defined with Kubernetes general Kubernetes resources. And finally, final step is to activate operator and custom resources by giving the YAML definition to Kubernetes. So there are several Kubernetes commands for activating each of YAML, but not so complex. So after activating the custom definition and APIs, we can find the ports of DPDK application. In this case, our SPP so can be found. And the operator itself is also launched as a port. And we can inspect operator's log by using kubecontrol logs command. And so it is so detailed also describing in shortly. A controller start the operator itself and launch DPDK container application and confirm DPDK application is running properly as defined in controller. And when state of application is changed, reconciliation process is automatically running. And we can inspect this behavior by inspecting the log. And so we have already implemented a prototype of our Kubernetes prototype for SPP. And here is a snapshot of demonstration. In this case, we can run the DPDK application pods properly, and we can see each of containers by using Kubernetes management application. And here is a summary and references. Yeah, that's all. Thank you.
So we have maybe time for one question.
Yes.
How are you planning to maintain API/ABI compatibility with the changing Kubernetes version with your code generation model?
Basically, Kubernetes is strongly keeping the backward compatibility, and we don't need to care about the different operating the version not so seriously. And so if there is some critical updating in the Kubernetes, so surely we need to modify the application itself. So yeah.
And this operator framework is open source. You have it available in GitHub.
Operator SDK itself, yeah, is open source. Yeah.
Thanks.
Thank you.
Thank you.
Thank you very much.